Hi, this is Lakshmanachari, working as Assistant Professor in Department of Cybersecurity, Institute of Aeronautical Engineering, Hyderabad. In this lecture, we are going to discuss the modes of data transfer between the CPU and the I/O devices. So, the digital computer system mainly it has three functional parts that are CPU, Central Processing Unit, memory subsystem, and I/O devices or I/O subsystem. So these are the three main important functional parts of the digital computer system. So already we know. So the CPU it performs various operations, and the memory subsystem it can be used to store some programs and data. And similarly, the I/O subsystem. So the I/O subsystem it provides an efficient communication of the CPU with the outside world. So because the user can communicate with the CPU only through the some I/O devices. So already in the previous class we have seen about the I/O interfacing. So in this, so see here. So here the using the I/O devices, we are connecting different I/O devices with the CPU, Central Processing Unit, because the user can interact with the computer using various I/O devices. But here, these I/O devices or peripherals, we cannot connect directly with the CPU because there are some differences that are exist between the Central Processing Unit and the I/O devices. So that is the reason. So in order to overcome the differences, so what are those differences? So we have mainly different different types of differences are there. That are, first one is the nature of operation. So the nature of operation for the CPU is it is in electronic in nature, but whereas the I/O devices they have the electromagnetic or electromechanical in nature. So that's why their nature of operation is different from the CPU to the I/O device. So that is the first difference. So next one is a data transfer rate. So the CPU it can execute the instructions at million instructions per second. That means the data transfer rate of the CPU is very high when you compare with the I/O devices, because the I/O devices the speed is obviously slower when you compare with the data transfer rate of the CPU. So the data transfer rate is the second difference. And coming to the third one, that is a data format. So in general, the data which is transmitting from the I/O device, it will be in the bytes. When the data is transferred from I/O device to CPU or from CPU to the I/O device, so then the data transfer will takes place in the form of bytes. So one byte is equal to a group of 8 bits. So in that way, the data will be transferred from either I/O device to the CPU or from CPU to the I/O device. And the last difference, So the last difference is it is operating modes. So operating modes. So the operating modes of the CPU is different from the operating modes of the I/O device. So these are the different differences that exist between the CPU, Central Processing Unit, and the I/O device. So to overcome that, differences, so we are using a interface. So we are using a interface circuit between the Central Processing Unit and the I/O device. Okay. So this is a necessity of the interface. So see here. So modes of data transfer. So binary information received from an external device is usually stored in memory for later processing. So whenever we the information or data which is received from external device is usually stored in the memory for later processing. and information transferred from the central computer into the external device originate in the memory unit. And the CPU merely execute the IO instructions and may accept the data temporarily, but the ultimate source or destination is the memory unit. So whenever the IO device it transmits the data, then that will be stored in the memory, and also whenever the IO device it receives the data, then it will be originate from the memory. Okay. So here we have seen the data will be transferred from IO device to the CPU or from the CPU to the IO device. So the data transfer between the central computer and the IO device may be handled in variety of modes. So in different ways we can transfer the data from IO device to the CPU or CPU to the IO device. So in that modes, some modes may use the CPU as intermediate path, and some other modes they will remove the CPU in the path. So that means without need of the CPU, the IO devices directly they can transfer the data to the memory. So these are the different modes. So the data transfer between the central system and peripherals it will be handled in mainly three modes. So the first mode is a programmed IO data transfer mode, programmed IO, and second one is a interrupt initiated IO, and third one is a direct memory access. So these are the three important data transfer modes between the CPU and the peripheral devices. So let's see one by one. So first one is a programmed IO. So programmed IO. So programmed IO. So that means suppose if the CPU execute program. So program means a collection of instructions. So by executing all the instructions of the program, then the program will be executed. So that the programmed IO operation or result of IO instructions written in computer program. So here by executing some IO instructions, then the data transfer will be initiated. So then that is called programmed IO operation. Programmed IO data transfer. That means as the name it specifies the meaning. So programmed. So programmed means a set of instructions. So by executing that a set of instructions, IO instructions, then that corresponding the data transfer will be takes place. Okay. So because we are using different IO instructions. So what are the different IO instructions? We have in and out. So these are the two different IO instructions. So in is used to read the data from the IO device, and out is used to send the data from the CPU to the CPU or memory to the IO device. So using these two instructions, IO instructions, then we can it can initiate the data transfer. So usually the transfer is to and from the CPU registers and peripherals. So here in the data transfer, usually the data is transferring from CPU to peripheral or from peripheral to CPU. So other instructions are need to transfer the data to and from CPU and memory. So already we have seen. So in and out instructions are used to transfer the data between the CPU and the IO devices. Similarly, we can also transfer the data between the CPU and the memory. So we can use this. Okay, we can use this. So store and load. So using these two instructions, we can transfer the data from CPU to the IO devices. So transferring data under program control requires constant monitoring of the peripherals by the CPU. So here in the programmed IO, the CPU has to continuously monitor the peripherals. So in this programmed IO, the CPU has to continuously monitor the IO devices, whether the IO device is ready to transfer the data or not. Okay. So once the data transfer is initiated, the CPU is required to monitor the interface to see when the transfer can again be made. Okay. Okay. So here, this is a scenario of the data transfer from IO device to CPU. So here we have a IO device. So we are transferring the data from IO device to the CPU through the interface. Through the interface. So already we know the interface is used to overcome the differences. Okay, to overcome the differences between that exists between the CPU and the IO devices. Okay, so see here. So IO device. So whenever the IO device is ready to transfer the data, then it will place a data in the IO bus. So IO bus, input or output bus. So when it is ready to transfer, so IO device will place the data in the IO bus. After that, the IO device will send a signal data valid signal to the interface. So whenever the interface it receives data valid signal, it can understand that valid data is kept in the IO bus, so that the data register, okay, so the data which is available in the IO bus, it will be stored in the data register of interface circuit. So the data that will be stored in the data register. Once the data register it contains some data, then the status register. So the status register, it is having a flag bit, it is represented with F. So when the data register it contains some data, then the flag bit will be set to logic 1. So the logic 1, F is equal to 1, it indicates that the data register it contains data. So when F is equal to 1, then the CPU it can understand that the data register is having some data, so that the CPU can read the data through the data bus. Okay, so in this way the CPU can read the data from the IO device. Okay, and next we have a address bus. So we have a address bus. So the CPU will initiate the address, because every IO device it is having some unique address. So using that unique address only, the CPU can access that particular IO device. So this CPU will generate the IO device address, and that will be placed in the address bus, so that it can access that particular IO device. Okay, so see here. So suppose if the see, and after the interface, after the data register is loaded with the data, then the interface will send a acknowledgement signal to the IO device. So that is a data accepted. So data accepted. So that means the IO device can, upon receiving the data accepted signal by the IO device, it can understand that the data which is sent in the IO bus has been received by the data register. Okay, and see here. So when the CPU when the CPU is read the data which is present in the data register, after that the flag bit will be set to logic 0. So F is equal to 0. So when F is equal to 0, see, the IO device it can send again one more byte of information to the interface. Okay, so when F is equal to 1, the IO device it cannot transfer the another byte, because already the data register it contains some data. So whenever that data is accessed by the CPU, so that the F flag bit will become 0, so that the IO device can transfer one more byte of information to the interface. Okay, so in this way the data can be transferred from the IO device to the CPU. But here the main drawback with this programmed IO data transfer method is, so the CPU, it has to continuously monitor the flag bit. So continuously it has to monitor the IO device, whether the IO device is ready to transfer or not. Okay. So so that the CPU's some considerable amount of the CPU's time is wasting here, because the CPU, it has to execute some important programs and the corresponding data. But here, instead of executing programs, the CPU is spending more time on checking the flag bit. So it is a wastage of CPU's time. So that this is the main drawback with the programmed IO data transfer. So to overcome the drawback, we are going for the interrupt initiated IO. So in the programmed IO method, the CPU stays in program loop until the IO unit indicates that it is ready for data transfer. So this is time consuming process, because it keeps the processor busy needlessly. So already we have seen what is the drawback of the programmed IO data transfer. So to overcome that, we are using the interrupt initiated IO data transfer. So this problem can be overcome by using interrupt initiated IO. So in this, when interface determines that the peripheral is ready for data transfer, it generates an interrupt. After receiving the interrupt signal, the CPU stops the task which is in processing and service the IO transfer, and then returns back to its previous processing task. So you can understand this with this diagram. Okay. So what will happen? So when the IO device, it is ready to transfer the data, then the interface circuit will generate an interrupt to the processor or CPU. Okay. See here. So this is a IO device. Then we have a interface circuit, and then we have a CPU. Okay. So in the interrupt initiated IO, when the IO device is ready to transfer the data, then the interface circuit will generate an interrupt. To the CPU. Okay. So what will happen? Upon receiving the interrupt signal by the CPU it stops its currently processing task, and then it will stores the return address, and then it will go to the ISR program, interrupt service routing program. So see here, interrupt. What is interrupt? So interrupt is it is something which breaks the routine. Okay. So interrupt or exception causes CPU to transfer the control temporarily from its current program to another program. So that is a interrupt handler or ISR. Okay. So see here. Let us assume the CPU is executing some main program. So this is a main program. So main program, it consists of several instructions. So let us assume at a point of time, at instruction I, we have there is an interrupt occurred at the memory location. At the instruction I, there is an interrupt occurred. So what will happen immediately? So the CPU, it stops currently executing program. So that means it stops the executing of the main program, and the program control will be transferred from main program to the another program, which is nothing but ISR program, interrupt service routine. Then the CPU will execute this ISR program, interrupt service routine program. After completion of this, again it is coming back to the main program where it was interrupted in the main program. Okay. So the interrupt is occurred at ith memory location. So after executing the ISR program, again it is coming back to the next memory location of the where the interrupt occurred. So what is the next memory location? I plus 1. So there the I plus to the I plus 1 memory location, the control will be transferred after executing the ISR, which is corresponding to the IO transfer. Okay. So here in this method, only so when the CPU will involve in the data transfer only when it receives a interrupt signal. Until it receives a interrupt signal, the CPU it can execute its important program. Okay, so that the efficiency of the CPU is improved here in the programmed in the interrupt initiated IO. Okay, so that is the main advantage with the interrupt initiated IO data transfer. And coming to the third one, so that is a direct memory access. So already we have seen total 3 modes of data transfer are there. First one is a programmed IO data transfer, and the second one is the interrupt initiated IO data transfer. So in these 2 methods, the CPU will be in path of the data transfer, but whereas in the third method, that is nothing but the direct memory access. So in this, we are not the CPU will not involve in the data transfer. So that means we are sending the data from the IO device to the memory without involvement of the CPU. So that means through the CPU, we can transfer a small amount of data. So large amount of data, the CPU cannot handle. Okay, so that's why we are bypassing the CPU. So that means we are transferring the data from IO device to the memory without involvement of the CPU. So that large amount of data we can transfer. So let's see its operation. So removing the CPU from the path. So that means here in this, when the data transfer takes place, we are removing the CPU from the path and letting the peripheral device manage the memory buses directly would improve the speed of transfer. So this technique is called DMA. So that means direct memory access. So as the name it specifies, it can directly access the memory. So the IO device can access the memory directly. So that is called direct memory access. So in this, the interface transfers the data to and from the memory through the memory bus. So a DMA controller manages to transfer data between peripherals and the memory unit. So this DMA controller, it will manages the data transfer between the IO device and the memory unit. So here in this process, the CPU will not involve. And many hardware systems use DMA, such as disk drive controllers, graphic cards, network cards, sound cards, etc. It is also used for intra-chip data transfer in multi-core processors. In DMA, CPU would initiate the transfer, do other operations while the transfer is in progress, and receives an interrupt from the DMA controller when the transfer has been completed. Okay, so that entire operation you can understand with this diagram. Okay, so here see, so it is IO peripheral devices. So these are the IO peripheral devices: DMA controller, CPU central processing unit, and RAM. So this is a main memory, RAM, random access memory. Okay, so here we are transferring the data from IO peripheral to the memory. So we are transferring IO device to memory directly without involvement of the CPU. So for that, what are the different sequence of operations to take place? Okay, so see here. So when the IO device is ready to transfer the data, so first it will send a DMA request. When the IO device is ready to transfer the data, it sends a a DMA request to the DMA controller. So then the DMA controller will come into the picture. So as soon as it receives a DMA request signal from the IO device, so then the DMA controller will send a bus request signal to the CPU. So this is a bus request. So it will send a bus request signal to the CPU. Upon receiving the CPU bus request, okay, then the CPU will relinquish the buses. That means the CPU is associated with data bus, address bus, write, read control signals. So this is data bus, address bus, and read and write together we can consider as a control bus. So the CPU will release all its three buses: address bus, data bus, and control bus. That means the data bus, address bus, and control bus of CPU will be released. So that means it will disconnect the buses from the DMA controller. So that after releasing all the buses, then the CPU will issue a bus grant signal to the DMA controller. So this is a DMA, this is a bus grant. So that means the bus grant is active. So bus grant is equal to 1 right now. So that means when bus grant is equal to 1, the read and write signals are acts as a output lines, and that will be connected to the read and write of the DMA controller will be connected to the read and write of the memory. Okay. So when bus grant is equal to 1, the read and write signals are acts as output lines, and that are connected to the read and write of the memory. Okay. After that, when bus grant signal is equal to 1, then the DMA controller will takes the control of the data bus, address bus, and control buses, because the CPU has released its buses. So that now the DMA controller will take the control of all the buses. Okay. After taking the control of all the buses, the DMA controller will send a DMA acknowledgement to the IO device. Okay. So whenever the IO device it receives a DMA acknowledgement, then the IO device it starts data transfer. Okay. So see here. So here the memory read and write are connected to the read and write of DMA controller. Similarly, the address bus of memory is connected to the address bus of the DMA controller. Similarly, the data bus of memory is connecting to the IO device as well as the DMA controller. So as soon as the IO device it receives a DMA acknowledgement, then it starts data transferring, so that the data it can transfer, the IO device can transfer the data from IO device to the memory through the DMA controller. So that means in this process, in this data transfer, the CPU is not involved anywhere. Okay. So this is called direct memory access. Okay. So see here, whenever the data transfer is completed, then only the CPU will it will take the control of all these buses. Okay. So in this way, the data can be transferred from IO device to the memory. Okay. So that concept is called direct memory access. So here there are two modes are there. In two modes, we can transfer the data from IO device to the memory. So first one is a DMA burst transfer. DMA burst transfer. So what is DMA burst transfer? So a block sequence consists of a number of memory words, which is transferred in a continuous burst while the DMA controller is master of the memory bus. Okay. So see here. Suppose if the IO device wants to transfer some 100 bytes of data from the IO device to the memory. So in the burst transfer, all these see, when the DMA controller is a master of the data transfer, then this 100 bytes of data at a time in a single burst cycle, all the data will be transferred from IO device to the memory through the DMA controller. That means all the data we can transfer at a time. That is called burst transfer. BRUST, burst transfer. That is the first mode of data transfer. And coming to the second one, that is called cycle stealing. Cycle stealing. So in cycle stealing, it allows the DMA controller to transfer one data word at a time, after which it must return control of the buses to the CPU. The CPU merely delays its operation for one memory cycle to allow the direct memory IO transfer to steal one memory cycle. So that means the second method is cycle stealing. Cycle stealing. Okay. So in the cycle stealing, see, suppose if the IO device wants to transfer 100 bytes of data in the cycle stealing, so the IO device only it transfers in a byte by byte. So in cycle stealing, so that means the IO device first it will transfer 1 byte of data from the IO device to the memory. Okay, IO device to the memory. So after transmitting 1 byte, then the DMA controller, see, after transmitting 1 byte of data from the IO device to the memory, then the CPU will disables the CPU will disables the bus ground signal. That means the bus ground signal will become 0. Okay, so that means the CPU will take the control of all the buses. Now the buses will be controlled by the CPU. Then the CPU will do its task. After certain time, again the CPU will give the bus ground signal. So that means again the bus ground signal will be equal to 1. In this time, the IO device will transfer second byte. So second byte is transferred from IO device to the memory. Again, the CPU will disables the bus ground. So in this way, a byte, only 1 byte of data will be transmitted from IO device to the memory until all the 100 bytes of data transfers. Okay, so that is called cycle stealing. So why we have called cycle stealing method? Because see here, so the DMA controller will steals the CPU's buses. So that's why it is called cycle stealing. Cycle stealing transfer method. Okay, so these are the two methods of the two DMA transfer modes. Okay, so in this lecture we have discussed about the modes of data transfer. So total we have seen 3 modes of data transfer, that are programmed IO data transfer, and interrupt initiated IO data transfer, and the last one is direct memory access. So thank you.
Like, share and subscribe. Hit the bell icon for more updates.